particles in a box. So a simple physical model. So if you consider like Bloch wave functions for a periodic semiconductor, so you have your periodic atomic potentials and your plane waves. But once you go down to a particle in the box, your plane waves essentially just turn into a standing wave, so it's a sine function. And your wave functions have your typical solution for a particle in the box. And you can interpret the energies for photoinduced holes and photoinduced electrons using particle in the box solutions, or approximate them as using the standing waves. So this color figure shows the valence band where you have occupied states, and then these very narrow figures show the density of states for your particles, and then these boxes just show what the wave function or the envelope function. So you have your particle in the box, and you have for your lowest exciting, for your lowest state, you expect spherical symmetry, and then your next bands you expect p orbital symmetry. And so we'll come back.
Question.
Yes.
So in your particle in box, what exactly is this U sub n of r? What is this function?
N of r.
U sub n of r.
Oh, it's just a periodic potential, so it's like the atomic lattice sites.
No. This is a wave function. So what is this U?
Talking about this one here, right?
You mean atomic function in the vicinity of atom?
Yeah, like atomic orbitals. Site-centered atomic orbitals, essentially, is how you can interpret it.
So it's not literally a particle in box, right?
Not literally, so you can, so these don't show the U parts, they show the envelope functions, but if you made this transparent, you would have like quickly oscillating parts inside of those. So these plots just show the envelope functions. Whereas if we wanted to do these U of N's, they're complicated, so we use software to compute what those are, which we'll get to. So it might not seem relevant now, but I just made this slide, so I'm going to call back to it later in some slides.
Satisfied or not?
What?
Are you satisfied? The equation before the arrow is for bulk. Equation after arrow is after applying confinement.
Is there concern that because it's not really a particle in a box, the energy wouldn't just be kinetic energy?
Well, if it's literally particle in the box, then the wave function is proportional to sine kr, with k is being quantized given the energies that are shown. And I'm just curious what exactly is the physical mode. Okay, I don't want to disrupt the talk, so we'll talk about it later.
Okay. So that's just considering if you put photoexcited carriers in a box, and then typically nanocrystals, they're more covalently bonded, or they don't have ionic charges in them, but these perovskites are a little bit more unique because they're polar crystals. And so instead of excitonic contributions being more dominant in these, it's going to be polarionic. Or polarons are going to be more prevalent to form in the excited state than excitons. And that's mostly due to the very high dielectric screening in these materials. So Coulomb interactions decay very quickly, so electrons and holes are going to be screened by the lattice sites compared to being able to talk to each other. So that's just comparing what these two figures here are comparing. And so if you have very little dielectric confinement or small dielectric confinement, you have a photoexcited electron in a hole, and they can be more or less delocalized, and they can interact with each other, while these lattice sites are charged. They don't move very much from the equilibrium. But compared to if you have polaron formation, you can see that these electron and holes states become a lot more confined. So if you have your electron here, it's going to be pulling positive nuclei towards it more than repelling negatively charged nuclei away, and vice versa for the hole. And so essentially what that does in your spatial coordinate is it localizes your charges into two distinct regimes. And notice that these bound, or you consider them as bound states, and they have these lines represent like electronic states for the bound polaron. And so this is just kind of introducing the idea of polarons in these perovskites, and so the Hamiltonian for polarons in general, if you want to think about how to describe the electronic structure of these, is the Froelich Hamiltonian was the first Hamiltonian used to describe these. So this was back in 1950s in second quantization form. So basically, it's made up of three parts. You have your on-site electronic states. You have your independent phonon modes here, and you have the cross-termed electron-phonon coupling, because you put the charge in and it interacts with the nuclei, so it gives this cross-term here. And so the on-site energies, those correspond to summing up just all your electronic energy. So N is your band state, K is your momentum, and S is your spin density. So you just create a state with a certain energy value. And same thing with your phonons. So you have your phonon momentum and band density. It has a certain energy and occupied. And then your cross term, this is just the matrix element of the cross term. So you have an electronic state interacting with the phonon state. And for these solutions, the analytical solutions are very hard to come by. So a lot of solutions, they use perturbative or variational schemes. So it introduces this alpha parameter, which people use to characterize the strength of the electron-phonon coupling in these solutions. And this kind of indirectly determines the size of the polaron. And so instead of looking into analytical solutions to these, because I'm a pretty simple guy and I haven't done final path integral, so it's kind of hard to understand the literature on this, but a simple way to understand the bound electronic states in these polarons is just to consider a Coulomb interaction. And so this is from a paper by Walter Cohen back in the 1950s. Basically, the point of this paper is that he found that if you introduce an electron or a hole into a semiconductor, you can reformulate the many-body problem into an effective mass problem. So basically, you just have an effective mass with a Coulomb interaction, and that describes the electronic state of the added charge interacting with the nuclei around it. And so any sort of Coulomb problem, we know what the solutions to those look like. They're going to be analogous to the hydrogenic solutions. So if we have our polaron bound states, that's what these represent. This represents the 1 over R potential, and these bands represent polaron electronic states in the confinement well. You could approximate or think about these just similarly as you would for a hydrogenic solution. And the energy spaces for each of these states would be some sort of scaled version of the Rydberg energy, like the energy of your lowest polaron hydrogenic state.
So
Mhm.
you have an electron, it polarizes the material around us. That's the polar one.
Yes.
And then it interacts with it.
So this paper doesn't include the ionic movement, but you can think of it as, you could just do a self-consistent scheme.
What is the hole in the box? Can you describe polaron electronic structure as an electron hole interacting? So is the hole the polarized charge of the surrounding atoms? Is this how we should think about this?
The way I think about it is you still have your independent electron hole. So you photoexcite, you have your electron and hole.
Okay.
But they just interact with different nuclei states because you have positive and negative nuclei charges. So the hole is going to interact more with
Nuclei tend
negative.
to be positive.
Say that again?
Nuclei tend to be positively charged. Electrons tend to be negatively charged.
I guess these are they're ionic charges. So it can have a positive or a negative. So like halides, they take an electron, and so they have an overall negative charge in the lattice. So ions can have positive or negative.
Well, you can shift the charge charging around, and you will have a build-up of positive charge and negative charge there.
Exactly.
What?
Exactly.
So maybe the term nuclei is a better term, because nuclei is just made of the, like, it's not just the nucleus, it's the nucleus and the valence electron atom around it. And so some atoms, they can take an extra charge, and so in the lattice, they'll have an overall negative charge.
So first, polarons can be created without a photoexcitation. Charges can be injected, either positive or negative.
Right.
And here he is considering response of a lattice to the injected charge and self-consistent response of this injected charge to the change in the lattice.
And that response is this effective whole. Is this?
In some community, instead of effective Hall or effective electron, people use the word polaron.
Right. And that's what creates this hydrogen-like level.
Exactly.
It's fine.
And so it becomes bound, and so it's maybe just looks similar to a Coulomb problem.
So I mean, you can have like electron polaron or home polaron, depends on the energy system. I'm just confused a little bit about the term hydrogenic that you use there, because when I think about hydrogenic state, I'm thinking about, let's say, silicon doped with aluminum or silicon doped with phosphorus, and it introduces a very shallow defect near the band edge. And if you look at the wave function, it's very standard, it's very delocalized. So when we think about polaron, we think about a lot, much more localized wave function, right? So
I guess
I'm a little bit confused about the equivalent between that polaron wave function and hydrogenic wave function. Oh, maybe you are right, but just that, I'm confused about the name.
And so polarons, you can have a lot of different sizes, so there's different regimes.
Yeah.
So the ones in these materials, like experimental,
Large polaron,
they're
we're
very
talking
large,
about
like
large
9
polaron,
nanometers.
yes.
So it's not a very bound state, so it has a deeper well,
Yeah.
or not, it has a shallower well. And then in these, I guess I'm not sure of the exact binding energies, but just from initial computations, it's around 1 eV binding. So it's stronger than like a dopant impurity, but it's still less than the hydrogenic.
Yeah.
So it's like, it's an in-between,
Right.
essentially. And so we can have electronic states introduced due to a polaron. And when people are researching these in the 60s, looking for solutions, one paper I came across found that for an appropriate coupling value, in the paper they found from 2.5 to 6, that these bound states are stable enough, so you can treat them perturbatively compared to like any sort of excitation that you do to them. And so since you can treat transitions between these polaronic states perturbatively, you can determine rates between these polaronic states using essentially Fermi's Golden rule. And so for this presentation we'll be talking about, or this illustration here is simulating like absorption spectrum. So you can have a series from this polaron ground state to this relaxed excited state, and so forth going up. Or you can even have in a couple of conduction path states. But you can also have non-radiative transitions. So if you had photoexcited, they would cascade down too. And so this is essentially what we're going to be trying to be modeling with our atomistic models. And this figure just shows experimentally for a close cousin material for the ones we're looking at. So they have a little bit different chemistry. And they're not nanocrystals, they're thin films. But they do pump probe experiments to look at time-resolved IR spectra. Here, so essentially the simple idea is they pump it, so they photoexcite it at a high energy, like 2 eV, to create the polaron. And then they probe it with IR frequencies to look for absorption characteristics. And just due to the different chemistry, they see a temperature dependence for polaron absorption, but the results from here indicates that they do see polarons in these materials. And so the next slide just kind of outlines, based on everything that we've done over here, what we're trying to model for dynamics of these systems. And so ionistic model, what we want to do is model the photo excitation from the conduction band, or valence band to conduction band. Monitor the carrier cooling to what's called in the literature usually the polaron relaxed excited states. And you can have two different things. You can have an electron or a negative polaron, that we call it a positive polaron. And then once they relax to these relaxed excited states, we want to try to determine the non-radiative and radiative transitions between the relaxed excited states to the polaron ground states. And so this is like our end goal for what we want to model. But we're going slowly and a little bit more methodically, so we break them up into just a negative polaron and positive polaron first. So, which we'll see later in the presentation. And so just some methodology for how we do electronic spectra for these materials. So we have to use non-collinear function, or DFT for these, and I'll explain that in a second. So basically, what this equation does is it sums over spin states for the materials, and you get, and for some materials you get spin mixing, so spin's not a good bottom number anymore. And so the solutions to this non-collinear one electron equation is a spinor cone check orbital, or a spin orbital. And it's just a two-component vector that's made up of a spin alpha or spin beta, or spin up and spin down components. And they obey the usual rules that you expect for good orbitals. So they have normality and orthogonality. And the reason that we have to use non-collinear orbitals is because in perovskites they have big relativistic effects due to lead orbitals that experiences large spin-orbit coupling. And so within the software that they use, they incorporate relativistic effects. So you have special relativistic effects in spin-orbit coupling. And spin-orbit coupling is the big one because for LEDs, it has a very high angular momentum state. And that's what this L represents, the mixing of angular momentum with the intrinsic spin. And so that's why we have to use spinners, so because the spin states are mixed. And this will have important consequences for the electronic states and kinetics in these materials. So those are the orbitals, and then these are the observables, the ground state observables we compute. So we have density states, we compute absorption spectra using the spinners, so we compute the transition dipole between two orbitals, which feeds into oscillator strengths. And oscillator strengths are just a probability of photoexcitation between two states due to coupling to electromagnetic wave. You can make an absorption spectra from that, and then I'll just note that from the oscillator strings we can compute a radiation of lifetime using Einstein coefficients for spontaneous recombination. So that's a charge neutral model, so with no polaron. And then to model electronic structure of polarons, we do the same calculations. So we start from a neutral model. And so that's the independent electronic energy and atomic energy, or phonon energy. So that comes from a charge neutral configuration for N electrons. And to approximate the cross term, the electron phonon coupling, we either add or remove charges from our model system, or add or remove electrons. And then we let the model optimize this delta R around the new charge. And so it changes the atomic positions due to the new charge. And so that's how we approximate the polaron formation. And then there's a similar group earlier, or reported this year, that uses a similar methodology as we do. And this is just an example for a positive polaron. So we remove one charge. So we create a whole state, and then we just re-optimize the model around that charge.
Sorry, question.
Mm-hmm.
So keeping the occupancies fixed in
change occupancies.
Why making a chart and not just fix the occupancy, one whole occupied whole state and one occupied part of the state?
So that's the end goal. So that's to model photo excitation. That's what we'd have to do, but we're doing it piecewise. So we can imagine injecting a hole, and then eventually it becomes a positive polaron. And then we also compute doing the opposite, so injecting an electron into the conduction band, and it forms a polaron. And then, so we're gonna get two independent models first, so we can see how the systems observe independently.
So it's that you assume no interaction between electron polaron and hole polaron.
Right. So we're just trying to isolate if we do see emission from these states, whether it comes from the whole polaron or the positive polaron or negative polaron. So we just do this to be systematic.
Intentionally exclude possible electron-hole interaction and look for purely positive polaron, purely negative, and as a next step, if resources allow to see if they can coexist.
Technically, do you introduce background charge to make sure everything is overall neutral?
It is included in the software package, yes.
So those are the orbitals that we use to compute some observables, and then I'll just go over how we model the dynamics in these systems. And so we want to model electrons and phonons interacting with each other that give rise to heat dissipation. And so if you do that, or if you set up the time-dependent Schrodinger equation for that problem, eventually what you run into is this cross-coupling term here, which is called non-adiabatic coupling. And essentially what it does is you have two different electronic states, I and J, and due to time evolution of the nuclei, it mixes them. And that gives rise to heat dissipation and non-radiative effects in these systems. And so this is just a Dirac notation, and then this term here is just showing the spinner, showing how we're using spinners to compute non-adiabatic couplings. And just to emphasize that so you update a time step for one of the orbitals, and you compare it to the previous orbital. And so whatever overlap that they have, that's kind of proportional to the transition rate between those two orbitals due to heating. And so this is the most competitive aspect of the modeling that we do. So this is first developed in the group in 2018, and since perovskites require the spinor orbital formation, we've applied it to model perovskite systems. And so that's the novelty behind this. And then what we do to convert these non-adiabatic couplings into rates is there's just a standard procedure of taking your autocorrelation functions of the non-adiabatic couplings. So you measure essentially how fast they decohere, and then you take Fourier transforms and convert them into rates. And in these rates, we incorporate into what are called Redfield tensors. And so this is just the density matrix theory that describes electron-phonon interactions and rates of heat dissipation. And so this Redfield tensor provides the dissipative transitions for the density matrix. And this is just the time evolution of the density matrix from the Liouville-Neumann equation. And another thing to note is for non-radiative lifetimes, we can approximate the non-radiative recombination as just the matrix element corresponding to the HOMO-LUMO transition or whatever non-radiative transition we're looking for. And just to give an idea of what this Redfield tensor looks like, so it's basically just a matrix, so corresponding to matrix of orbital i's and orbital j's with matrix elements, so that's what this z-axis represents. And the height of these bars represent the rate or how fast that the transition occurs between two electronic states. And so essentially, So this block right here corresponds to HOMO minus 24 to HOMO. So that essentially determines how fast holes cool. So hole cooling rates, and then these correspond to conduction band states. So these describe how fast an electron would cool. So those are the rates that are used to compute excited state dynamics. And so now we'll get on to the results, which